Hello, welcome to Math 209, the fundamental concepts of mathematics. Today's topic has to do with the historical overview of mathematics, in particular that of set theory. So, we will first look at some of the basic concepts of set theory. Let us begin with its definition. This is defined by a particular mathematician, Zermelo, and he said that set theory is the branch of mathematics whose task is to investigate mathematically the fundamental notions of numbers, of order, and of functions in their original simplicity, and to develop thereby the logical foundations of all arithmetic and analysis. So the question of constructing sets will be discussed in this class. In particular, how do we construct the set of real numbers, the set of rational numbers, the set of natural numbers, so on and so forth. But basically, when you talk about sets, this is defined as follows. You simply gather together all the elements in one set having the same property or having a prescribed property. And this prescribed property is defined by a particular function. In this case, we have the function p of x. So let us consider some of these questions. Are these sets? So for example, the first one, the set of all sets. So meaning we are together in one set all of the sets we can think of. So let us consider, for example, let me choose to change the color of my pen into, say, black. So let's consider we have the set, say, a sub 1, say another set, a sub 2, and another set, a sub 3, and assume that all of the collection of sets that we can think of are finitely many, say a sub. So you gather this together as one set. So let's put these together and let's define this to be our set A. So the question is this collection a set? And second, is the set A an element of itself? So since we are looking at A to be a set of all the sets, so therefore it must be a member of itself. Second, how about this set? The set of all sets that excludes itself. So is this set a set? So these two examples can be considered as set or as sets if we only consider this definition of a set having to collect together elements having the same property. So, however, in this class, we will have the following topics. The first one, we will talk about or review about logic. I know you have already discussed logic in your math in the modern world, but in our discussion in our fundamental concept of mathematics, we will be further studying these logics and apply this in our methods of proving. And we also talk in this discussion about the principles of mathematical induction. And also, we will be discussing about the axiomatic set theory. Remember the definition of sets which we have presented earlier, that you simply gather together all of the elements having the same property? There's a problem with that definition. And we will be discussing that problem in this topic. And we will talk about the axioms that somehow prevent that said problem. Third, we will be discussing about relations and functions, but in this time we will talk about these topics in terms of sets. And fourth, we will also talk about how do we construct number systems. In particular, this discussion, we will look at how natural numbers are being constructed. And also, in addition to this topic, we also talk about integers and divisibility of integers and the complex numbers. And lastly, among this discussion and the fundamental concepts of mathematics is what if you have a set or a set of numbers, then you put a structure on that set, say addition and multiplication. So what can we come up about it? So we have a system of numbers. So at this point, or at this topic, we will talk about groups, rings, integral domains, and fields. So that you can answer this very basic question that came out a few weeks ago again in the internet on the problem of 8 divided by 2 times 2 plus 2. Now, to really look at understanding about infinity, let's quickly look at these two examples. The first one has to do with this set of natural numbers. The set of natural numbers at this point, let's consider 0 as a member of the set of natural numbers. So we collect these numbers and denote this with n. So the set of natural numbers are composed of 0, 1, 2, 3, so on and so forth. But however, we consider as well a subset of this set of natural numbers. At this time, we consider the squares of each of the elements. So you have 0, 1, 4, 9, 16, so on and so forth, or in general, the elements and square. So the question is, which among these two sets has more elements than the other? So the question is it set of natural numbers because you say that the whole is greater than its part, or maybe you say that it's A because this is a trick question. So how do we count sets? So basically, when you talk about counting set in a finite manner, you simply, for example, if you have the set A composed of 5 elements, you just simply count 1, 2, 3, 4, 5 elements. What if you have a set B composed of 1, 2, 3, 4, 5 elements? And you say that both sets have the same number of elements, so they have the same number of elements. So, however, what if we consider correspondingly one element with another by having a one-to-one correspondence? So this element with this element, this element with this element, or this element with this element until this element with this element. We can do that as well with the set of natural numbers and its subset. That is, we map 0 with 0, 1 with 1, 2 with 4, which is 4 is the square of 2, 3 with 9, 4 with 16, so on and so forth, with n squared. So you have a one-to-one correspondence with the set of natural numbers and with the set of these squared elements. So at this time, I'll repeat my question. So which of these two sets have more elements than the other? Now, how about let's consider another example. Let's look at the set of numbers between 0 and 1 and put them in a real line like this and subdivide this number line from 0 to 1 by the following elements of 0 to 1. Say 1 half, 1/4, 1/8, 1 over 16, 1 over 32, so on and so forth. So having these points fixed from 0 to 1, you consider now the length of the line segment generated by these points. Let's name them as L sub 1, L sub 2, L sub 3, L sub 4, and so on and so forth. And let us denote the same letters in terms of the length of these line segments. Now, what is the sum of the line segments L sub 1 plus L sub 2 and so on up to L sub n? We're talking about the lengths of this line segment. So, intuitively, the sum of these line segments are actually less than 1 for all elements n. Well, with that intuitive notion, we thought, well, it's okay. But however, what if we take the limit of S sub n as n approaches infinity? So how do we do that? So let us again look at our line segments. What are we adding with S sub n? Well, first, L sub 1 is just simply the length is 1/2, and L sub 2, its length is just 1/4. L sub 3, the length is just 1/8. L sub 4 is just 1/16, so on and so forth. But what we are adding is the following. So let me change my pen into this color. So we have S sub n to be the sum of 1/2, then 1/4, then 1/8. Since we have indexed this with n, we are summing up to L sub n, the length of L sub n, which is 1/2 raised to n, based on this pattern. However, we can somehow find a close formula in terms of simply looking at this length of sum by having a simple formula for S sub n. What we can do is to multiply both sides of this equality by 1/2. So we have 1/2 times the left-hand side, S sub n, and the right-hand side, as you multiply each term with 1/2, you will have the following. 1/2 times 1/2 is 1/4 plus 1/2 times 1/4 is 1/8. 1/2 times 1/8 is 1/6, 1/16. So you have that here, so on and so forth. You have an expression of 1/2 raised to n minus 1. You multiply that 1/2, so you will have 1/2 raised to n. And the last term, you are multiplying this with 1/2, so you will have 1/2 raised to n plus 1. Then what you can do is to take the sum of the left-hand side and the right-hand side. So you will have, or not the sum, but the difference of this expression and this expression. So you will have the difference 1 minus 1/2, or this is simply 1/2 times S sub n. And this is equal to, the right-hand side is simply 1/2 minus 0 is just 1/2. But individually, each of these terms are just the same, so the difference are just 0. But you are left with 0 minus 1/2 raised to n plus 1. So you will have 1 over, or the negative 1/2 raised to n plus 1. But again, this is just simply 1/2. Divide both sides of the equality by 1/2. You are left with S sub n to be 1 minus 1/2 raised to n. So this will be somehow our closed form of the expression, the sum of the lengths of those line segments, or the powers of 1/2. But the question, let's go back to our question earlier. We are interested with the limit of S sub n as n approaches infinity. Or this is simply by taking the limit of 1 minus 1/2 raised to n as n approaches infinity. But this is just simply, remember, 1 is just independent with n, so therefore we can simply pass through the limit. But the second term, this is a power of n, so therefore as n approaches infinity, the denominator gets bigger and bigger, so therefore the whole expression, the fractional expression, approaches 0. So therefore this is 0. If you review your calculus discussions in your calculus 1, so therefore you will have the limit of S of n as n approaches infinity is equal to 1. So if we go back again with our question as to what is the limit of S sub n versus in the intuitive definition of what's the sum of this line segment, would that give you different answers. So the question of infinity has been a problem before this mathematician, Georg Cantor. Georg Cantor is said to be the father of set theory. He pioneered the understanding of infinity. in fact, he actually give us the idea what really infinity is in terms of collecting the sets, infinite sets. Say, for example, the set of natural numbers. Is it the same as the set of integers? Is it the same as the set of rational numbers? Or is it the same as the set of real numbers? And Cantor said that there are different sizes of infinities. In fact, you will be learning later that the set of natural numbers is the same as the set as integers, but different in terms of the set of real numbers. So meaning to say there can be infinitely, or at least two different sizes of infinities. However, during his time, there was a problem of accepting such an idea. However, in the long run, people in the mathematical community accepted these facts. I'll give you a link on the description below regarding the life of Joris Cantor, and you may look at his work in particular with this development on set theory. Now, let us quickly review some of the rudiments of set theory which you have learned maybe when you were in your senior high school or in your math in the modern world class. Again, let us go back with how we define our set earlier by simply looking at the collection of all of the elements having the same property. So therefore, in this case, we simply let A to be the collection of X with the property P. Now, there are some points to consider, and let us enumerate them as follows. So first, will always set exist? So this is some kind of a philosophical question on the existence of sets. So what are the sets? What can be considered as sets? Second, what is an empty set? If you go back in the history of mathematics, zero has not been accepted as a number zero until it was the Indian who pointed out that zero is exactly a representation of a void or of nothingness. So if we go back as to the notion of sets, is an empty set a set? Is this really real? So how do you define an empty set in terms of this logical expression of a set? Then finally, what is a universal set? Is this really a set? So what is the universe of the universe? So what somehow covers the universal set as a superseding set of such a set? So these are the questions that you can think about given this definition. But let us continue by looking at some of the basic ideas of some operations involving set. The first one is the notion of the union of two sets. We simply define this as the property having to put X either on set A or on set B. Well, you can simply represent this notion of a set as follows. So what if you have the union of B? Wait, let me point out where's my pen. Okay. So my pen is here. So let us change this into black color. So remember, we can represent set if you can recall your description of the Venn diagram by simply putting these sets together as close figures. Say this is set A and this is set B. And the union of these two sets is that X can belong to either A. So you can shade the set A, or this can belong to B. However, when you talk about the intersection, so kindly let's change this. This is the intersection of A and B. So the property that we are talking about, the intersection has to do with X belonging to both A and B. So therefore, if we again go back to our diagram having the closed figures A and B, so X must belong to A, and at the same time, it must also belong to B. So therefore, that area can be described by this shaded portion. Now, how about set difference? Meaning, X must be an A. If this is A, this must be an A. However, it must not, oops, again, let's go back to our, you have the set B. So it must belong in A, but not in B. So therefore, the area that we are describing the difference of these two sets is this area. Okay, how about set complement? But at this time, we look at where does this set subscribe into or covered by. So let us consider a universal set U where A, the set A belongs to. So it must belong to a universal set U, but not on the set A. So therefore, you can shade this portion of your universal set. How about how will you say that two sets are said to be equal? As long as every element of A must belong in B. So therefore, if this is set A and this is set B, if the elements of A are as follows, so if we describe them finitely as point A, point B, point C, and point D, for these two sets to be equal, so therefore you will have A here, B, C, and D as well. But we can further formalize such a definition after we describe certain axioms that involves the definition of sets. Now, how about set inclusion? How will you say that A is a subset of B? As long as logically you can describe it this way, that if X is in A, therefore X must be in B. So therefore, we can somehow describe it as follows. So if your set B is here, so everything in A must be in B. Now, let's go back to our question earlier. So, will set always exist? So, when we base this in terms of our definition, that you simply collect all of the elements having the same property, therefore, you have a set. Well, you can say yes by this definition. But how about an empty set? How will you define an empty set? You can consider this logical statement, this property, that you simply say that X is, remember, if we symbolize our empty set as this notation, the null notation, X is an element of the null set is false. So meaning what we are saying here, the belongingness of X to this set null is always false. So that will be our property X to describe an empty set. And finally, how will you define universal set? So question, if you have a set A, this is the universal set enveloping set A. So what is the universal set of the universal set? Can you simply say that simply this universal set, let us denote this as A sub 1, a U sub 1. How about what is the universal set of the universal set U sub 1? So you might say it must be U sub 2. So if we describe this way, there might be, you can say that infinitely many universal set enveloping one universal set 2. the other. So it might somehow be confusing if we still make use of this definition of R set. So the next meeting or the next discussion, we look at sets in terms of its infiniteness and its sizes. So we will describe set in terms of how it is to be denumerable or non-denumerable. And one of the favorite topics I usually talk about when you talk about set theory is the continuum. That is the interval from 0 to 1. And you assign a number of infiniteness on this continuum. We simply use the letter C on this, and we will prove that this set is non-denumerable. Or, in other words, this is uncountable. And we will also discuss by next meeting or next discussion about Cantor's first theorem that talks about the infiniteness of the infinities. So again, at this time, so see you next meeting.